All right, 12. 12 is like a weird one, and this is just kind of like Regents Prep. This is one of those you can just read and snap answer, but I'll kind of explain it to you in the meantime. It says after a reflection, that's one of those transformations, and up to this point we know translations, which is slide, rotation, which is like a spin, and we also know a reflection, which is a flip, okay? So they're telling us, look, after a reflection, you're going to get this image, right, that A prime, B prime, C prime, and it came from this original one, that ABC. It's saying, here's like A, B, C. No matter what kind of reflection you do, all right, why is it that those triangles will be congruent, the exact same size? And all you have to say is, well, when you do a reflection, the only thing that changes is like its orientation or its position. Or even better, you can say, when they say explain why triangle ABC will be congruent to its image, triangle ABC will be congruent to its image, triangle A prime, B prime, C prime, because a reflection preserves or keeps the same, preserves shape and size. In other words, if you want a fancy word, if you're too lazy to write that out, you can say a reflection is an isometry. Okay, iso is Greek for equal, and metry is size. So when you write that down, well, why are these triangles congruent? That's because reflections are isometries. They're things that preserve size, they keep size. If you buy that, stop the video. I'll see you in the next one. If you want to kind of see why that is, why is this even a question? What transformation doesn't do that? Why are they asking this? I'll quickly go through it here. We got a triangle here, and let's do it like that, okay? And here, all of these are transformations, right? And if I were to reflect this about that, you see I've got these triangles, right? And the way you're going to tell if triangles are the same size is like you could look at their area. Polygon 1, this first one, area 5. Polygon 2, that's area 5. So they're the same. You can see that. Well, that's reflection, right? Size is preserved. What happens if I were to rotate this? Sure, 120 degrees, it doesn't matter. You can still see that these triangles are in fact congruent, the same size. I'll make it blue for this one. You can see here their area is the same. No size changed, right? And the only other one we know of is if we were to translate. We're using this fancy term vector. It just means take this shape, translate it about a point, some amount in the x direction, and then some amount in the y direction. All right, and it just shifted, and you can once again see that. Let's make this purple. When we look at its area, its size, look, they're all the same size. The only one, which you haven't learned yet, and you'll learn next chapter, the one that changes size. These three transformations are called rigid transformations. They don't change size. It's rigid. The only one that's going to change size is what we call a dilation. If I were to dilate that object about a point by a factor of, let's call it 2. Factor of 2. That shape got a lot bigger. And you might be saying, well, it should be the area, right? If the original area is 5, the new area should be 10. I don't think it will be 10. I think it's going to be 20. Yes, there it is. Look at that. You know math, good to go. Yeah. Your gut's going to tell you, oh, just, If I dilated this by 2, it's going to grow by 2, but getting ahead of myself. Dilation is the only one that changes its size, and there's a little reason why it's not getting doubled. It's getting something else. It's 20 now. Went too long. I'll see you in the next problem.